Alright, hello everyone. It's Dre again, back to explain part 2 of this exam. So now that we've gone through the scaling and we've got our initial guesses, we can kind of start going through our coding in Python in order to use our initial value problem solver to get some gradient profiles of the mole fractions in order to make a plot. So what I'll do first is I use our numerical solvers. I'm importing them all here from different databases. We have NumPy, which is numerical Python as NP, as well as the SciPy tools for integrating for the initial value problem and also optimizing for the root problem that we use later on, as well as the Plotly tools in order to make our plots at the end. So what I first did is outline the parameters of the problem. These are the Stefan-Maxwell diffusivity constants, which I turned into meters squared per second rather than the millimeters squared per second in the book. I outlined the pressure and temperature, the ideal gas constant, delta, which is the length of the Stefan tube, which is 0.24 meters. And then what I wanted to do is calculate the concentration based off the pressure, the ideal gas constant, and the temperature, which I did here. And then I also defined these variables f, 1, 2, 1, 3, and 2, 3. These are just to make our code a little bit simpler, so we don't have to keep constantly referring to the concentration, the diffusivity constant, and delta. So F is defined as the concentration times the Stefan-Maxwell coefficient divided by delta. And then I also outlined the initial parameters of the mole fraction of acetone and methanol, Y1I and Y2I, as well as our initial guess from the scaling technique for the molar flux of acetone and methanol being 10 to the negative third. So now what we want to do is we want to define a function, we'll call it dy, with the dependent variable eta, which to remind you is the z over delta, ranging from 0 to 1, or from 0 to 0.24 meters in this case. And so then we also want to define our independent variable of y. And so what we want to do is just make it a little bit easier on me so I don't make any typos, is we want to define y1 as the first element in the array, which, to remind you guys, in Python, your indexing starts at 0. Okay, and then also the mole fraction of methanol, as the second value of the array, which is y1. And then we can also define the mole fraction of air to be 1 minus y1 minus y2. And that's just by definition of the mole fractions all having to add up to 1. Next, we want to return the array of the Stefan-Maxwell equations that we have. And so what you do here is you type in the different equations we have, which I am going to refer to my notes real quick. But basically, you have your Stefan-Maxwell equations, which is your mole fraction of acetone times the molar flux of methanol minus your mole fraction of methanol times your molar flux of acetone. And that's going to be divided by that value that I made earlier of F12. And then that's all going to be subtracted by your mole fraction of air times your molar flux of acetone divided by the value of F13. That's your first equation. And then you're also going to want to define your second equation in this array, which would be the mole fraction of methanol times the molar flux of acetone minus the mole fraction of acetone times the molar flux of methanol. And that's going to be all divided by the F12 value. And then you're going to subtract mole fraction of air times the molar flux of methanol divided by the F13 value, or F23 value, sorry. And that looks good. So what this does is returns our two Stefan-Maxwell equations into an array so that we can then turn it into an initial value problem. And with the initial value problem, we want to use the solve IVP function, which, as you can see, calls for a function, and then which is our dy, and then a t-span, which in this case is more of a distance span for us, but it's your eta range, which is from 0 to 1, forgot parentheses, and then it wants an initial guess y0, and in this case this is our initial guesses for our mole fractions, which we defined as y1i and y2i. And then you can define a method for solving, which we use the method Radal. And then you can then you want to define your dense output equal to true. And what this allows you to do is evaluate at a certain point. So now if we shift enter, cool. So this worked, and we have now an array for our mole fraction of 1 and 2, or acetone and methanol. So you have all of these are the iterations for acetone as it's going from that liquid interface up to the air blowing over it at the top of the tube at delta, and this is the mole fractions for component 2, or methanol. But you can see here that near the top, so you're going for, so this is the initial and this is the final, it's going to a negative value, which doesn't make sense, first of all. But we know that at the top of the Stefan tube, your components of acetone and methanol should be essentially 0 because it's pure air blowing over top of it. So you can assume that the mole fractions of 1 and 2 are equal to 0. So now what we need to do is provide values for our molar fluxes so that we can then use those to converge our values for the mole fractions to equal 0. So first let me put this in this function, and we're just going to call this as variable res, and what we can do is evaluate our initial value problem at so res dot sol at 1, and what this is going to do is solve for your mole fractions at eta equal to 1, which is when the values should equal 0. But just to show you what we're getting here, well, anyhow, at our point currently, they do not equal 0. So we need to get a function and use our root solver in order to have these converge to 0. But first, I'm going to define a function f with the variable of the molar flux. And what I'm going to do is define molar flux of acetone equal to the first value of the array, like I did with the mole fractions, just to make it easier on me so I don't make any typos. And then I'm going to indent these so that it is vested within this function. And then that should allow me to, that indent does not match any outer indentation level. I think these need to be indented to, okay, sorry about that. And then now we can see that we still have the issue of the values not being the same. So we want to use the root solver, which we'll do that down here. We can just say the result of the root, which the root wants you to provide your function, which in this case we just gave the function of f, and then it wants the initial guesses, which we defined originally as n1i and n2i. And what this is going to do is then allow you to find the point at which the mole fraction is equal to 0. Sorry, my computer crashed while I was doing that last part. So what we're doing here is we defined our function, or our variable res, as the root function. And what we could do with this is going to then create an array. So at res.x with our correct molar flux guesses, or our correct molar fluxes, I guess. So our initial guesses were incorrect, as we could see, because our mole fractions weren't converging to 0 as they should have been. So what this does is this gives us our correct molar flux values for n1 and n2. So what I'm going to do is store those as n1 and n2 by looking at the array values of the root function. And then what we want to do with these is then use our function that we had previously here to calculate our new mole fraction values, which in this case should be 0. But this should work. Okay. And so I can delete this. And so now with this function, we can use the correct molar flux initial guesses in order to then create a concentration profile correctly. So what I'm going to do is create a data plot value. And that's going to be equal to numpy dot linear spacing, which is just going to create equally spaced points, and we're going to go from the range of eta, which is from 0 to 1, and we want 51 evenly spaced points between those values. And we're going to solve our equation at those eta plot values here. Make sure I iterated that. Iterate this. Cool. Okay, now what I want to do is make some subplots for this to see the concentration profile. So we're going to create a figure, and that's equal to make underscore subplots, and it wants you to define the number of rows and columns, which we want 1 row and 1 column. And then what we want to do is add the trend line, which is going to be using the function called fig.add underscore trace. And as we defined up above, the graph objects, we use the shorthand go. So the shorthand for a scatter plot is in this first graph object and scatter. And then with the scatter plot, you need to define your x values, which our x values are going to be the eta plot, and that's those linear space values for eta. And then our y values are going to be equal to our function. And in this case, this one is going to be for acetone, so we want to use the first value in the array, and we can name this acetone. And we want to do the same thing for our methanol and air so we can get them all on the same plot. So we're going to change this to the first value in the array, and that's going to be methanol. And then instead of making a third variable, we can just do use the definition of mole fractions and have 1 minus the mole fraction of acetone minus the mole fraction of methanol. And what this should allow us to do, crossing our fingers, probably help if I spelled things right. Name y is not defined. Y is not defined. Oh, okay, yeah, so I accidentally used the y values here, but we want the solution values for each in this case. And that should fix that. Cool. And so yeah, now we have the plot of the concentration profiles of acetone, methanol, and air. And this looks right. So the way you can kind of tell is you have your initial mole fractions of methanol and acetone, and this is at your liquid boundary. And as you go across towards the delta, 0.24 meters, in this case we're looking at eta values though, so it's a 0 to 1 range. At the opposite end, so the top of the tube, you should essentially have no acetone and methanol, and that should be equal to 0, which we see here, because it is going to be purely air blowing across the top. So that would wrap up this problem, and thanks for watching.